Hey guys, today we're going to talk about logs and log functions. Up to this point, you've already learned about exponential functions, right? And exponential functions. Alright guys, up to this point, you have learned about exponential functions. Remember when we did exponential functions, we took them in the form f of x equals b to the power of x, right? And that looks like this, f of x equals b to the power of x. We're going to learn about a different type of function today called a logarithmic function. And it is related to the exponential function in that they are inverses. Now at this point, we're not actually going to work on them as inverses. We're going to work on log functions as their own standalone functions, and we'll talk about the relationship between them as you learn more about them. Okay. Now, I do need you to remember what you've learned about exponential functions because we are still going to use that definition. Okay. Here's how we define what a log function is. An exponential function that's written more or less like the one you see, but written as y equals b to the power of x. When we find the inverse, which is what we're going to find the log function to be, we remember switch the x and y value. So we end up with x equals b to the power of y. Now, if I'm going to define that as a log function, let me show you what I'm talking about here, okay? Remember, we had the exponential function y equals b to the power of x, which we wrote its inverse, which is x equals b to the power of y. If I'm going to write a log function, okay, my log function is going to look like this. It can be written as a version of this x equals to b to the power of y function like this. You can write it as y equals log of a base b x. Okay, so one thing I want you guys to remember is this vocabulary. This b right here is known as the base, and you'll hear me refer to that a lot. So remember that particular vocabulary word. There are some rules here about these log functions. All right, b and x must both be bigger than 0. Okay, b must be greater than 0. Sorry, I meant to write x there. X must also be greater than 0. In other words, if you're looking at that function, okay, you must also realize that x can never be negative, or you cannot take the log of a negative number. The other thing is that b cannot equal to 1, okay? B cannot equal to 1, and that's a rule that we're going to follow, and we'll talk about that later when we talk about how these functions came to be. All right, so when this is true, b is greater than 0, x is greater than 0, and b is greater than 1, then we can say that log base b of x is defined as the exponent y, okay, is defined as the exponent y that makes the equation b to the y equals x true. Okay, so it's defined by the exponent y, which makes this equation b to the power of y equals x, okay, true. Now, what do we mean by that? What I'm looking for when I talk about what I mean by that is this idea. All right, let's say that I have a function that looks like this. Log base b of x equals some y. So let's use some real numbers. Let's say that my b is 4 and my x is 64. Remember our rules that b has to be greater than 0 and it can't equal 1, and that x has to be greater than 0. These follow those rules. So if this is true, then log, I'm going to write my base as 4 and my x as 64 equals some y value. Okay, now, one thing I want you to realize is that a base can be any number value that's out there as long as it's positive. Okay, for now it needs to be positive, and we'll deal with the potential of negative later. But the base must always be positive, right? That is our b greater than 0 rule that we are trying to follow. It also can never equal 1. Okay, so if this is true, then what I'm looking for here, remember, it makes the equation b to the y equals x true. Okay, so what I'm looking for here is I'm looking for a relationship to where when I take 4 and I take it to the power of y, I get 64. So I like to think of it as a path that I'm traveling in a circle. 4 to the power of y equals 64. Now, this, of course, reminds you of your exponents, where you take 4 times itself, however many times, equals 64, and we know that 4 times 4 times 4 times 4 is 64. So in this case, y is equal to 4. So to make this equation true, then what we can say is that log base 4 of 64, whoops, sorry about that, is equal to 4. Okay, so we can try another example. Let's look at a different one that's written a little bit differently. Okay, let's suppose then that I write it this way. Let's suppose that I ask you to write a logarithmic expression given an exponential one. So let's suppose that I write 3 to the power of 3 equals 27. And I tell you that I want you to write it as a log expression, right? I ask you to write as a log. Now remember our general form that says log base b to the x equals y, right? We've got our little circle pattern going on where b to the power of y equals x. Let's plug in the pieces here that we know, right? We know that the b has to equal 3. Okay, because we're looking for, remember, the rewritten one where b to the power of y equals x. Okay, and so what we're looking for here is our base. Our base here, okay, is 3, right? So we're looking for 3 to some power, right? And fortunately, they've already given us that power, okay? That's 3. Right, 3 to some power is here. That's that y. Okay, and it equals x. Right, that's that 27. So if I want to write it as a log, then I can write it this way. Log base 3 of 27, right, is equal to 3. Okay, so now we can write exponential and logarithmic functions. We can go back and forth. All right, so what about if we want to solve an equation using logs? Let's see if we can do that. We've got to learn some properties. Okay, so here's a property of equalities for logs. Remember, b must be greater than 0, and b can't equal 1. Okay, and on top of that, if this is true, then the following is true. Log of some base x, if it equals log of some base y, then x must equal to y, right? And this makes it incredibly convenient because then what we can do is we can say that x and y are equal to each other. So for example, let's look at this one. Let's say that I have a log base 2 of x squared minus 4, and that's equal to log base 2 of 3x. Now, if they are the same base, right? If they are the same base here and here, and they're both base 2, then I can say that x and y are equal to each other. So we're going to make x and y equal to each other. So we're going to set the equations equal to each other. All right, so we're going to set x minus 4 equals 3x. We're going to make them equal to each other. So now here's the key. Remember all that stuff that we learned on factoring a few weeks ago? We have to use it again, because the only way we can solve for this equation is to make it equal to 0. And so we're going to make it x squared minus 3x minus 4 and make that equal to 0. Now that that's happened, you can choose to solve this however you'd like. You can factor it, okay, or you can use the quadratic equation. I'm actually going to factor it. I find that just a little bit quicker and a little bit easier, and this factors out into x plus 1 times x minus 4 equals 0. So now remember, we can solve this by saying x equals negative 1 or x equals 4. All right, so we're not finished yet, because remember, we have these rules up here at the top, right? Up here at the top, we have these rules that say that b has to be greater than 0 and b can't equal 1. All right, and we already know that that's true because they're base 2. But then remember, from the very beginning, we also have the rule that x and y also cannot be negative. So we've got to check that, right? So let's check our equation. So let me remind you what our equation was, right? It was log base 2 x squared minus 4 equals log base 2 of 3x. And on the previous page, we've discovered that x equals either negative 1 or x equals 4. Okay, so let's check our solution here. Okay, if x equals negative 1, let's see what happens. All right, I take negative 1 squared, I subtract 4, and it equals to 1 minus 4, which is negative 3. Now, this should be a red light for me, right? This cannot be true. Why? Because if this value up here is negative 3, I'm violating one of my very first rules, which is that I cannot have a log. I cannot take the log of a negative number. I just can't. Not allowed. Okay? So that actually gets rid of x equals negative 1 as one of the solutions. So let's go ahead and hope that x equals 4 actually works. Okay? So let's take log base 2 of 4 squared minus 4, and that equals log base 2 of 16 minus 4, and that equals log base 2 of 12. Now, I realize that right now you don't know what log base 2 of 12 is, and that's okay. What I want you to understand is these rules that they have to be positive, and so let's check the other one, right? Log base 2 of 3 times 4 is equal to log base 2 of 12. So you can see actually that they are in fact equal to each other, which is great. That is exactly what we're looking for. So we do have a solution in the x equals 4. We just can't use the x equals negative 1. All right? Now, let's look at one more set. Let's look at properties of inequalities. The same rules generally apply, except there are some rules for when things are less than. So let's look at this. If, whoops, sorry about that. Let's switch back to our black ink here. If, same rules, b is greater than 1, x is greater than 0, okay, then you have two choices. If this is true, and you have log of base b of x, okay, is greater than y, then your solution is going to be this. X is greater than b to the power of y. Okay? If, same rules, b is greater than 1, x is greater than 0, but log of base b of x is less than y, okay, then we have to make some adjustments here. All right, we need to make some adjustments to where then this falls between 0 is less than x is less than b to the power of y, so that we don't violate these rules of what x what that log value can be, right? A log value must be greater than 0, okay? So let me show you what I'm talking about here, okay? Let me show you one of these equations. So log base 5 of 2x plus 1 is less than or equal to log base 5 of x plus 4. Okay, so when I'm looking at this, I want you to notice a couple of things, right? We need to notice a couple of things here. First of all, this is a less than or equal to sign, which means that we actually want to use this equation here, or this inequality, I'm sorry. Okay, so that tells us where we're going now. The other thing I want you to notice is, remember, we have these rules that tell us about what the value in here can be. Since we have these rules about what those values can be, we already know that both of those have to be greater than 0, right? Which tells us that this value has to be greater than 0, and it tells us that this value must also be greater than 0. And if that's true, then x has to be greater than -1/2, and in this case, x has to be greater than -4. Okay, so let's start there. So now we're going to use this particular set of rules to solve this inequality, okay? And we're going to solve it just like we would normally. We're going to say that 2x plus 1 is less than or equal to x plus 4 because of our rules, okay? And so what we're going to find here is that if I subtract x from both sides, I end up with x plus 1 is less than or equal to 4, so x is less than or equal to 3. Now, we're almost done, but not quite, right? Why aren't we done yet? We're not done yet because we have to take into account these parts, right? Now, if it's greater than -1/2, it will be greater than -4. So we really just need to look at this one here, okay? So we need to limit our solution to all values where -1/2 is the smallest thing we can achieve, and it's less than or equal to x, and it's less than or equal to 3. You're going to try some problems on your own, and I'll help you along with them. The next time we get together, we will talk about some properties of logs.